Good afternoon, everyone. Today, I'll be discussing important concepts and knowledge in the topic chemical bonding under the A-level chemistry syllabus. Here are the content which I will go through them. This topic is an important topic in the A-level chemistry syllabus because it covers many important concepts that can be tested in the examination. Now, these are the learning outcomes or the assessment objective for this chapter. Okay, you can refer to the A-level syllabus for the details. Now, what is chemical bonds and the octet rule? Chemical bonds are the binding forces of attraction between particles, atoms, ions, or molecules, and result in lower energy arrangement. The formation of a bond involves the redistribution of the outer electrons of the atoms concerned. The octet rule states that atoms will tend to lose, gain, or share electrons until they have 8 electrons in their valence shell, which is the outermost electron shell. They do so to achieve the same number of electrons as the noble gas closest to them in the periodic table. All noble gases except helium will have 8 valence electrons. Noble gases have high ionization energies, low affinities for additional electrons, and in general, unreactive. However, there are exceptions to octet rule, meaning it is possible for a molecule to have atoms beyond 8 electrons or lesser, or having odd number of electrons. We shall look at them individually. All ionic bond is the electrostatic attraction between two oppositely charged ions. The ions are formed by the transfer of electrons from the metallic atom to the non-metallic atom, usually. Metallic atoms have 1 to 3 valence electrons. By losing these valence electrons, they become cations and have a stable octet electronic configuration of noble gas, just like sodium and calcium. These are the IE equations we learned in the previous chapter on atomic structure. So before you learn bonding, you have to master atomic structure. Okay? Non-metallic atoms usually have 4 to 8 valence electrons. Atoms of elements from group 15 to 17 accept electrons to form anions and also achieve stable octet electronic configuration, just like fluorine and phosphorus. The energy transfer during the formation of magnesium oxide can be illustrated using the dot and cross diagrams, where the magnesium loses 2 electrons to form Mg2+, and the oxygen atom gain the 2 electrons to form the oxide ion. A magnesium atom loses 2 valence electrons to form magnesium ion, while oxygen atom gains 2 electrons to form oxide ion. The electrostatic attraction between the oppositely charged ions is known as ionic or electrovalent bond. Now, these are the steps to draw the dot and cross diagram of ionic compounds. Number 1, write down the correct chemical formula of one formula unit, for example, sodium sulfide. Write down the symbol representing the metal and enclose it within square brackets. Determine the number of valence electrons lost from this metal atom and write the charge on the cation. Beside the completed cation, write the symbol represent the non-metal and use dots to represent the number of valence electrons in this atom. Determine the number of electrons gained by the non-metal atom for it to achieve octet configuration, and use crosses to represent these additional electrons. So, you have to use dot and cross diagram, with dot representing the electrons of one atom and cross the other. Enclose the non-metal in square brackets and reflect the number of electrons gained as the charge of the anion. Check the respective number of cations and the anions correspond to the chemical formula of the ionic compound. Write the appropriate number as a coefficient to the square bracket and do not write as subscript. And here this is the example. And there are more examples for your reference. Now, moving on to covalent bond. Covalent bond involve the sharing of electrons, where the electrons shared are localized between the two nuclei. The covalent bond is the electrostatic attraction between the shared pair of electrons and the positively charged nuclei, shown in the diagram. Covalent bonds are usually formed between two non-metal atoms. However, there are exceptional cases where covalent bond can be formed between a metal and a non-metal, for example, aluminium and chlorine. It is energetically unfavorable for non-metal atoms to lose electrons. By sharing electrons, the non-metal atoms achieve the noble gas configuration. In the structural formula, each covalent bond is represented by a straight line between two atoms. One represents two electrons. A structural formula shows which atoms are present and how they are attracted to each other. A dative covalent bond, also known as coordinate bond, is formed when the shared pair of electrons is provided by one of the bonding atoms. It is represented by the arrow from the donor atom to the acceptor atom, like NH4+. In this formula, nitrogen has two lone pair electrons after it bonds with the three hydrogen. So with the extra hydrogen here, it will share both of its lone pair with this hydrogen. So it looks something like this in the dot and cross diagram. So cross represent the electron of nitrogen, dot represent the electrons of hydrogen. And this plus means that electrons lost from hydrogen. The reason why electron is lost from hydrogen is because nitrogen is more electronegative. So it keeps the electron to itself to a greater extent. Hydrogen loses electron more easily. So when NH4+ is formed, the electron is lost from hydrogen, not nitrogen. And where does this electron goes to? It will goes to the non-metal atom. For example, chloride is formed. So this can come from here. I use another symbol to represent the electrons of chloride ion. So this from H. Okay. Now, but our focus here is on the dative covalent bond. One atom must have a lone pair of electrons. In this case, it will be the nitrogen in this context. Another atom, which is the hydrogen, will be the atom that receives or accepts the pair of electrons, and it must have a vacant, low-lying orbital. Now, these are other examples of compounds with dative covalent bond, like H3O+, hydrogen ion. Okay, so the two electrons from oxygen is shared with hydrogen in a dative covalent bond. And we have BF3 and H3. Dot means there is a dative bond between N and B. So when boron with 3 valence electrons are all shared with the fluorine, there is a vacant orbital that is ready to accept the lone pair of electrons from nitrogen. Now, in certain covalent metal chloride like aluminum chloride, they are dimerized, which means two molecules of the same compound react with each other Okay. So instead of AlCl3, we have Al2Cl6, which is a dimer. So there is two dative bonds shown here, where the chlorine with the lone pair of electron is able to form a dative bond with the aluminium. Aluminium have a vacant, low-lying orbital to accept the pair of electrons from chlorine. So if we examine the dot and cross diagram, this is how it looks like. Right? Okay, let's move on. What is the guiding principle in drawing dot and cross diagrams of covalent bonds? When atoms form bonds, they will achieve the noble gas configuration NS2 and P6, 8 electrons in the outermost shell where possible. So dot and cross diagram should be drawn such that the octet rule is obeyed by the maximum number of atoms, with the exception of the H atom, which can only hold 2 electrons in its valence shell, because hydrogen atom has only 1 electron shell, 1s2. Now, these are the general considerations. Number one, we need to identify the central atom and the side atoms. And the central atoms is usually the less electronegative atom that is less likely to gain electrons and tend to acquire electrons and form negative ions in chemical reactions. Then we determine the number of valence electrons of each atom, determine the number of bonds each atom needs to form in order to achieve octet where possible. Lone pair of electrons in the valence shell of the central and side atoms must be shown in the dot and cross diagrams. So the central atom for CH4 in this case is carbon because it's the less electronegative atom. And we have the 4 side atoms as hydrogen. Each hydrogen forms 1 single bond to attain a full valence shell. So there are 4 CH single bonds, and this is a structural formula of methane, CH4. For CO2, C can form full valence shell by sharing 4 electrons. This is how you represent it in dot and cross. 2 electron pairs are shared between C and O atom, forming a double bond. There are 2 CO bonds in CO2. In N2, nitrogen, each nitrogen atom can attain a full valence shell by sharing 3 electrons. 3 electron pairs are shared between 2 nitrogen atoms to form a triple bond. For NH3, the nitrogen is a central atom. Each hydrogen can achieve a full valence shell by forming 1 single bond with nitrogen. There are 3 NH single bonds in NH3. N has a pair of electrons in its valence shell, which is not involved in bonding. Now, in this case for NH3, although N is more electronegative, it is still the central atom because the number of N is lesser than H. Therefore, usually may not apply in all cases. Now, let's move on to dot and cross diagrams for charged species. For polyatomic cations, the electrons are in general lost from the less electronegative atom, since they are not holding on to the electrons strongly. And they are usually the central atom. For polyatomic anion, the electrons are generally gained by the more electronegative atom. And for charged species, we need to include the overall charge on the ion with square brackets drawn around the ion. So these are the examples, BRF2. So in this case, this is a charged species, all right? So bromine actually lost 1 electrons. So it has 7 electrons, but you can see from the dot and cross, it lost 1. So the bromine loses 1 electron. So octet structure is still achieved in this case. So for bromine, it has 2 lone pair, and fluorine retains the 3 lone pair for each atom. Because bromine is less electronegative, it will lose that 1 electron. NH4 plus, we went through that just now when we discussed dative bond. Okay, SF3 minus. So in this case, the ion is a negative charge particle. So since fluorine is more electronegative, it will gain the electron to form F minus. So one of the fluorine atom will gain, and it's represented by this. Can you see that? So you can use this, or you can use another symbol to represent electron gain. Either a hollow circle or a triangle. Okay, that will do. So sulfur, right? You'll notice that has an expanded octet. Why? Because it's in period 3, not period 2. So it can hold more than 8 electrons in its valence shell. All right. It goes on to the principal quadrant number n equals to 3, where it can hold up to 18. So 10 electrons is not an issue for sulfur. NO3 minus. So the electron is gained by the oxygen. Okay. NOF. So this is the order of electronegativity, where fluorine gain electron more easily, followed by O and then N. So between N and O, O will be the atom that gain the electrons. Okay. Either use this to represent the electron gain instead. So for the dot and cross diagram of NO3 minus nitrate ion, okay, nitrogen has 5 valence electrons. So out of the 5, 4 are shared with these 2 oxygen, 2 each. All right, and one of it is a dative bond. Okay, where nitrogen share both electrons, and this oxygen never share. But here, this oxygen share both electrons, and nitrogen share both. For here, nitrogen only share 1 electron because it only has 1 electron left to share, and oxygen will share 1. And in order to maintain its octet structure, octet configuration, the electron is gained by oxygen. Okay, so one of the O atom has gained an electron to form O minus, usually this one, and will form a single bond with N. Because it gains an electron, there's no need for oxygen to share both. So this only needs to share 1. So for O minus, right, the valency dropped to 1. So O, the valency is 2. It will share 2 of its electrons in bond. But O minus, because it gains 1 extra electron, the valency dropped to 1. Therefore, you only see a single bond between N and O here. Okay? One of the O atoms form a dative bond. N cannot expand octet, unlike sulfur in the earlier example. Okay? Now, you can try to draw the dot and cross diagram for HNO3, pause the video, and try yourself later. And check your answer. So this is the answer for HNO3. It's actually a molecule. It's not ionic compound, okay? But it dissolves in water and dissociates to form the H+ ion. But before that happens, it is a molecule. So for HNO3, it's very similar to this. You have a dative bond here. Okay, you have a single bond here. while this oxygen, okay, is bonded to another hydrogen here. So this is also single bond. Okay, and here is a double bond. So this is how you draw the dot and cross for HNO3. You have double bond, single bond, and dative bond. What are the exceptions to octet rule? Number one, molecules with less than 8 electrons in the valence shell, like BCl3 or barium chloride, such molecules are described as electron deficient, as more electrons can be accepted to achieve octet configuration. Number two, molecules with unpaired electrons in the valence shell, like NO and NO2, which we call radicals. So molecules with more than 8 electrons in valence shell, which is only possible for elements in period 3 or beyond. So in this case, we have expanded octet, just like sulfur. So for BCl3, in this example, we can see that boron only has 6 valence electrons after forming 3 single bonds. So this is an example of part 1 where the molecules are described as electron deficient. How about this, NO2? So nitrogen forms 1 double bond with oxygen and 1 dative bond with another oxygen. This is so such that nitrogen will not exceed its octet configuration. However, by doing so, we will have nitrogen having 7 number of electrons in the valence shell after forming the bonds, which means that it's actually a radical here, meaning there's an unpaired electron. So unpaired electrons implies that there's a radical. All right. For PCl5, this is another example of an element which can accommodate more than 8 valence electrons. All right, because it is an element in period 3. Any element in period 3 or beyond can accommodate more than 8 because there's an expanded octet. All right. Question: why is it that both NCl3 and PCl exist, but we only have PCl5 but not NCl5? Answer: period 3 elements do have vacant and low-lying orbitals, which is a 3D. Expansion of octet is only observed in PCl5 and in some compounds formed by elements of period 3 because the energy required to promote electron from 3s or 3p up to 3d is not very large. However, elements in period 2 do not have the vacant low-lying orbitals for expansion of the octet. Promotion of electrons to the next quadrant shell requires too much energy. So period 2 elements can only accommodate maximum 8 valence electrons. Now, we are going to talk about VSEPR, valence shell electron pair repulsion theory, which explains shapes of molecules. Covalent bonds are directional. So molecules or ions with covalent bonds have definite shapes. So VSEPR is used to predict the molecular geometry of a species. Electron pairs around the central atom of a molecule are arranged as far apart as possible in space to minimize their mutual repulsion. So lone pair repulsion, acid lone pair bond pair, and lone pair bond pair repulsion is greater than bond pair repulsion. So this is the theory that we use to predict the molecular geometry. Now, what are the steps involved? Applying VSEPR, draw the dot and cross diagram of the species. And remember to include the lone pair because we want to see if there's any lone pair repulsion. Count the total number of regions of electron density around the central atom to determine the electron pair geometry. So each lone pair or lone electron constitute one region of electron density. Single bond or coordinate bond constitute one region of electron density. So Each double bond or triple bond also constitute one region of electron density. Then we count the total number of lone pairs around the central atom and deduce the molecular geometry or shape of the species. For example, for BCl3, we observe 3 bond pairs in the valence shell of the central atom, which means 3 regions of electron density. So to minimize electronic repulsion, the 3 electron regions are arranged in a trigonal planar geometry around the B atom, which is the most favorable electron pair geometry. The molecular shape is trigonal planar with a bond angle of 120 degrees between the chlorine and boron. So boron is the central atom. So the atoms are arranged as far apart from each other to minimize repulsion. So this is a dot and cross diagram, not the molecular geometry yet. So what I'm saying here is that the angle between here, 120, 120, 120. Okay, so this is trigonal planar. These are the examples of the various shapes of molecules and polyatomic ions. Now, if we have 2 regions of electron density like this, it is linear. And these are the examples. The bond angle is 180 degrees. So in this case, there will be no lone pairs. All the electrons are involved in bonding. Now, trigonal planar, if there are no lone pairs like this, BF3 will be 120 degrees. However, if there is a lone pair on the central atom, like SO2, okay, the angle will be smaller because of repulsion effect. So it would be lesser than 120 degrees. Now, if we have the central atom bonded to 4 atoms, this shape is called tetrahedral. The angle is 109.5. If we have 1 lone pair, it's called trigonal pyramidal, which will be about 107 degrees. 2 lone pair is described as band, like water, 105 degrees as the bond angle. If we have 5 electron density, which include the lone pair as well, we call it trigonal bipyramidal. Okay, bipyramidal is different from this. All right. So like PCl5 is 120 degrees or 90 degrees. Okay. So 90 degrees is between this one, while 120 is here. Okay, that's what it means. If we have 1 lone pair, it will cause the shape to be a bit more distorted from trigonal bipyramidal. We call it seesaw because it looks like a seesaw, like SF4. Okay, sulfur tetrafluoride. Okay, we do not need to know the angle. If we have something like this with 2 lone pair, it looks like a T shape, right? Because of the 2 lone pair. So this will be 90 degrees. We call it T shape. If there are 3 lone pairs for 5 electron density, it will be linear. And this is a polyatomic ion. Now, moving on to the next one, 6 electron density around the central atom, octahedral, 90 degrees, like SF6, sulfur hexafluoride. If we have 1 lone pair, we describe it as square pyramidal. Because we have a pyramid, but it's squarish. So, yeah. And we have 2 lone pairs, square planar, 90 degrees between the atoms. Now, so the bond angle really depends on the repulsion between the electron pair around the particular central atom. So the closer the electron pair are to each other, the greater is the repulsion. Bond angles may hence deviate from the ideal, as different electron pair present may have different repulsions. So about the same central atom, the lone pair exerts greater repulsion than a bond pair. It is affected by only one positive nucleus compared to bond pair electrons, which are attracted by two nuclei. So that's the reason why lone pair has greater repulsion. Okay, because bond pair are attracted to two nuclei, but lone pair is attracted to one nucleus, so there is more repulsion. So in CH3, NH3, H2O, the number of lone pair of electrons around the central atom increases. So the deviation of bond angle from the ideal angle will be observed like this. So NH3 has one lone pair which repel the bond pair more strongly than bond pair repel each other. Hence, pushing them closer together. Because lone pair, bond pair, okay, is of greater repulsion than bond pair. So you can see that H and H here is closer. While H2O, right, you have actually two bond pair which repel each other to a great extent. So it pushed this thing even closer to 105 degrees. So in general, for similar electron pair geometry, which means 4 electron density, the bond angle will deviate more greatly from the ideal as the number of lone pairs increases. So this is BS-EPR theory. So you can try doing this, okay, before you check the answer. The dot and cross diagram for the various species, identifying how many regions of electron density, how many lone pairs, and the molecular geometry. So for SO2, okay, this is already provided for you because our focus is more on the number of regions of electron density. So there is a lone pair on the sulfur atom. So there is a total of 3 electron density and 1 lone pair. So this molecular geometry is band, or we can call it V shape. Okay, because there is lone pair bond pair repulsion, so it will look a bit distorted, a bit bent. As for SO3 2-, okay, there are 4 electron density with 1 lone pair, so it is trigonal pyramidal. For this, we have 5 electron density around the central atom, but there are 3 lone pair, so it is linear. For this, we have 6 electron pair and 1 lone pair, which is a square pyramidal. Now, effect of electronegativity of central atom on the bond angle. Repulsion between bond pair is also increased by the increase in the electronegativity of the central atom. So the more electronegative the central atom is, it tends to draw electron density or the bond pair towards itself to a greater extent. The bond pair electrons will be nearer to the nucleus and exert more repulsion. The bond angle will become larger. For example, NH3, PH3, ASH3. So you can see that there is a decrease in bond angle with an increase in the electronegativity value of the central atom, NP and AS. Because if the central atom has great electronegativity like nitrogen here, okay, it will draw the bond pair to itself closer, and hence will have greater repulsion, resulting in higher bond angle. Okay. But you must be very careful that you are comparing between similar trigonal or similar geometry, molecular geometry. Okay. Covalent bond between two atoms occurs when the valence orbitals of the two atoms overlap. The two orbitals can be either both singly occupied or such that one is filled with a pair of electrons while the other is an empty orbital, dative covalent bond. The overlap of atomic orbital must be effective so that electron density in the region between the nuclei is maximum. The overlap gives rise to a new orbital called molecular orbital. So consider this graph, which shows the variation in potential energy with the internuclear distance between two hydrogen atoms. So at this part here, the distance between nuclei is really very close. And hence there is great repulsion between the nucleus since they contain positive charges. So the energy will be very high. But as the distance increases between them, the energy will decrease until this point here, which we call the optimum bonding distance, where the molecule is most stable with the minimum potential energy. So as the two hydrogen atoms approach each other, okay, their 1s orbital overlap and the electron pair will spread out over both orbitals to form the British bonds. So as the distance between the nuclei increases further, where we see that the two atoms are so far apart, the energy of the two separated atoms will increase. All right? To reach almost zero. All right? Now, let's talk about sigma and pi bond. Depending on the way the orbitals overlap. Overlap means the orbitals come together and the electrons move between the orbitals, within the orbitals. So the covalent bond itself can be classified as either sigma or pi bond. A sigma bond is formed when two orbitals overlap head-on, head-to-head. So the electron density of the sigma bond is concentrated between the nuclei of the two bonding atoms along the nuclear axis. So we have SS overlap. The S orbital, okay, cannot have side-on. It can only have head-on, okay, because of the shape. So this is what happens. So when you have head-to-head overlap, and this is the sigma bonding orbital. For PP overlap, meaning we have overlapping of p orbitals, okay, they actually form sigma bonding orbital in this way. We have SP overlap, meaning we may have one s orbital overlapping with the 3p orbital to form head-to-head overlap. So we could have an atom with, let's say, hydrogen with only one s orbital, but chlorine with 3p orbital. So these two orbitals will overlap when they form the covalent bond. Okay, and we form sigma bonding orbital. So head-to-head is sigma bond. All right. But if we have something like this, pi bond, where the orbitals are overlapping collaterally, meaning they are side-to-side overlap, like this. Okay. So in this case, the pi bonding orbital has an electron cloud above and below the nuclear axis, but they have zero electron density along the axis. So there's no electron here. The electrons are concentrated above and below the axis. The pi bonding takes place when atoms undergo multiple bonding, like double or triple bond. One of the bond must be a sigma bond and the rest will be pi bond. So, example, a double bond, one of it is a sigma bond, the other is a pi bond. Okay, so in a double bond between oxygen, for example, we have the orbitals overlapping head-to-head, sigma, and we have the other bond above and below the axis, pi bond. As for triple bond, is one sigma and two pi bond. Okay? So sigma bond is stronger than pi bond because head-to-head overlap of charge cloud in a sigma bond has a greater degree of overlap than the side-to-side overlap. Okay, so this is a summary of what single, double, triple bond consists of. how many sigma and how many pi bonds. So you can try this question, okay? And then pause the video and get the answer later. So for this molecule, C2H2 is a linear molecule. So there is a triple bond between carbon. So how many sigma and pi bond are there? So this is a sigma bond. This is a sigma bond. And these two bonds in the triple bond is pi bond. So we have 3 sigma, 2 pi. Next, what is bond length? Bond length is the distance between the nuclide of two bonded atoms. The stronger the covalent bond, the shorter the bond length, because the atoms are brought closer to each other, shortening the bond length. The strength of a covalent bond is measured by bond energy, which is defined as the average bond energy absorbed when 1 mole of a particular bond is broken in the gaseous state. The molecule with strong covalent bond in general has less tendency to undergo chemical change than those with weak bonds. Nitrogen has very strong triple bond with a large bond energy. So if we want to break the triple bond, we need a lot of energy before it can react. Fluorine has weak FF bond because there is lone pair repulsion. So this makes this bond very reactive. So the strength of covalent bond is affected by this. Number 1, the number of bonds between the atoms, the effectiveness of overlap of orbitals, and the difference in electronegativity of the bonding atoms. So for the same bonding atoms, with increased number of bonds, the number of shared electrons between the two atoms also increases. So there's increased electrostatic attraction between the bond pair and the two nuclei, which increases the bond strength. So the strength of triple bond obviously is greater than double bond and then single bond. So these are the data. However, it is not twice as much between the double and the single bond because the bonds in double bond is a sigma and pi bond. Pi bond is weaker because the orbital overlap is less effective. So the bond energy of double bond is less than twice of the single bond because CC bond is a sigma bond, while CC double bond has a sigma and pi bond is much weaker. In general, more effective orbital overlap will result in a stronger bond. So this is the bond energy of chlorine to iodine. Now, if we talk about the bond strength, obviously chlorine is the strongest among the 3 based on the bond energy. So high bond energy means high bond strength, or strong bond strength. Because for chlorine to iodine, the overlap of orbitals will become less and less effective. So the bond energy decreases from chlorine to iodine. It has to do with the atomic size. So iodine is quite big. So the overlapping is not so effective. Now, let's talk about electronegativity difference. The electronegativity of an element measures the relative tendency of the atom to attract the shared pair electrons in the covalent bond. So based on Pauline's definition, fluorine should be the most electronegative element. So it's given an arbitrary value of 4.0, and all values of the other elements are relative to it. So the higher the value, the stronger the attraction. And electronegativity has this trend. Down the group, it decreases. Across a period, increases. Now, a polar covalent bond will result if the bond atoms have different electronegativity. And we will have partial charges arising on the two bonded atoms. For example, in HF, F is more electronegative than H, so it will attract bonding electrons more strongly. So the electron density distribution of the HF bond is asymmetrical, and the HF bond is polar, with F acquiring a partial negative charge and H partial positive charge. So when you represent the density of the electron, it is greater on the F side. So it's asymmetrical, not symmetrical, to show that the distribution of electron is not equal. In addition to the existing covalent bond, there is now an increase in electrostatic attraction due to the two partial charges, which lead to increased bond strength. So when the electronegativity difference gets greater as shown, the bond energy increases. Because when we have a greater difference in electronegativity, the covalent bond is more polar, there's greater bond polarity and hence stronger bond. So the bond polarity strengthens the bond due to additional attraction from the partial charges. There's greater electrostatic attraction now. You can try exercise 4 at your own time to rank the bonds in order of decreasing bond strength. So for this one, CO, C double bond O, C triple bond O, the triple bond should have the greatest electron density, as electrostatic attraction between nuclide and the shared electrons is the strongest. So their bond strength should be the highest, followed by the double bond. As for this one, we look at electronegativity difference. So it will be SF will be the highest because it's the most polar due to greatest different electronegativity. Yeah. And hence, more polar is the covalent bond. So largest electronegativity difference. All right. Then we have more polar or greater bond polarity and stronger bond. Most chemical bonds are actually intermediate between ionic and covalent bond. So we have ionic bond with some covalent character or covalent bond with some ionic character. Okay, the extreme end will be pure covalent bond here and pure ionic bond, but actually a lot of chemical bonds are here. All right. So this one will be this will be this. Now, for ionic bond with covalent character, the attraction of the cation for the valence shell electrons of the anion causes some distortion or polarization of the electron cloud in the anion. Okay, so polarization means the electrons distribution are distorted because one is attracting more to a greater extent. So the electron cloud will be pulled in the region between the two nuclei. So instead of a pure ionic bond, there will be some form of sharing electrons, which means there's some covalent character. So for example, this cation, it is pulling the valence electrons in the anion to itself. So there's some attraction towards the cation. And hence this electron density is between the ions. So there's some degree of covalency. So the cation must be polarizing, able to pull the electrons. The anion must be polarizable, okay? Able to let go of the electron to a certain extent. Not completely, but to some extent. So the more polarized the anion, the higher the degree of covalent character. So what does the degree of covalent character depend on? Number one, the polarizing power of the cation, which is the ability of the cation to polarize the anion, which depends on the charge density, charge over volume. So the higher the charge and the smaller in size of the cation, the stronger the polarizing power. Okay, higher the charge is quite understandable. Okay, but smaller the cation means that the valence shell electrons are closer to the nucleus. So the attraction is stronger. Like between these two, right, we will expect lithium chloride to be of greater covalent character because it's much smaller than sodium. So this is lithium smaller than the lithium ion, smaller than the sodium ion. As for this one is higher charge compared to the magnesium, and aluminum is actually smaller in size. Smaller size. It's smaller in size because it loses 3 valence electrons, so the remaining electrons are attracted more strongly to the nucleus. Because aluminum has more protons than magnesium, correct? So aluminum versus magnesium. So aluminum have 13 protons, magnesium has 12. But when the ions are formed, the electron 10 here is 10. So you have more protons attracting the same number of electrons in aluminum. Hence, it results in a smaller size due to a stronger electrostatic attraction between the nucleus and the valence electrons. All right. Also, we need to consider the polarizability of the anion, whether the anion is easily polarized, which depends on the charge and the size. So electron cloud of large anions are more easily distorted than the small anions. Like this is smaller, this is larger. Because for larger anions, they are not holding on to the valence electron so strongly. So more easily, not lost, but more easily given out. Same here, larger law. Yeah. Okay. Fajan rules of predicting high degrees of covalency. So it depends on whether the cation is small, anion is large, and the charges of both ions are high. So this is a question. Explain why aluminum fluoride is ionic, whereas aluminum chloride is covalent. So if aluminum chloride is ionic, the high charge density of aluminum ion will distort the electron cloud of the chloride to such an extent that electron sharing becomes predominant. So aluminum chloride is predominantly a covalent compound existing as discrete molecules. Okay? The reason why this cannot be ionic is because aluminum ion is of high charge density. So it's able to distort the electron cloud to such an extent that there is much more electron sharing. But if you talk about fluoride, it is of a smaller electron cloud and is therefore less polarizable. So the distortion will be less significant. So aluminum fluoride is predominantly ionic. In addition, the difference in electronegativity between aluminum and chlorine is smaller than between aluminum and fluorine. So this is another reason why aluminum fluoride is ionic and aluminum chloride is covalent. And if we consider another example of aluminum oxide, it is ionic with covalent character because oxide ion is still not so polarizable as it is much smaller in size. So when two atoms of the same type form a covalent bond, the electron pair is equally shared between the two nuclei. Since both atoms are of the same element, they have the same electronegativity. So in this case, both hydrogen have the same tendency to attract the bonding electrons, and hence the shared electron pair is equidistant between both atoms. When two atoms of different electronegativity form a covalent bond, the electron pair is not equally shared. So we have a dipole. The bond becomes polar. So this is a polar bond, where we have unequal distribution of electron due to different electronegativity of the elements. So it has some ionic character, but not an ionic compound yet. We call it polar covalent bond. Okay. The degree of polarity is measured by its dipole moment, which is a product of charge and distance between the charges. So this is the formula. So this is dipole moment. Q represents charge and R for distance. This is not required for A level. It's just for information. Okay, so the greater the bond dipole moment, the more polar the bond. The dipole moment is a vector quantity that has both magnitude and direction, which you learn in physics. It is shown by the symbol, this, where the arrow points towards the more electronegative atom. So bromine is more electronegative. It has a partial negative charge. So it is attracting the hydrogen to attracting the electrons to a larger extent. Okay. And we have the example of Cl and Br. This time around, Cl is more electronegative, so the arrow points towards Cl. As for this SO2, O is more electronegative, so it's pointing towards O. As for CO2, same thing. Now, this is a table that shows the bond length, electronegativity, difference, and the dipole moment of the various halide compounds. So we can see that the dipole moment decreases from HF to HI, which corresponds to a decrease in electronegativity. In general, the greater the difference in electronegativity between the two atoms, the greater is the bond dipole moment, and hence the more polar is the covalent bond. So what is polar molecule? So this is not a polar bond. This is a polar bond. All right. Then what is a molecule that is polar? Now, for a molecule made up of 3 or more atoms, both the polarity of the bonds and the molecular geometry determine whether this molecule has an overall dipole moment. The overall dipole moment of the molecule is a vector sum of all the bond dipole moment. So, if the molecule has an overall dipole moment not zero, then it is polar. If the overall dipole moment is 0, it is a non-polar molecule. So, molecules made up of atoms of similar electronegativity are non-polar, since the bond dipole moment will be 0. So the vector sum of the dipole moment is also 0. So you have the same element, it is definitely a non-polar molecule. Molecules made up of atoms with different electronegativity can either be polar or non-polar, depending on the structure, depending whether the dipole moment sum cancel off each other, meaning whether you have the sum of dipole moment equals 0 or not. If it's equals 0, non-polar. Not equals 0, polar molecule. All right. Now, SO2 is a band molecule, and there is actually an overall dipole moment. So, because the dipole moment is not 0, this is a polar molecule. But if you look at CO2, it's a linear molecule. It's non-polar. Why? Because if you look at the structure, although CO bonds are polar covalent bonds due to different electronegativity of the two atoms, the bond dipole moment cancel each other out vectorially. So the overall dipole moment of carbon dioxide is 0. Examples of non-polar molecules which are made up of atoms with different electronegativity. So these are examples of molecules with atoms that have polar covalent bond, but because their bond dipole moment cancel off each other, the net dipole moment is 0, they are non-polar, like this one. So this is an example here, right? So this is negative, positive. Okay, so here, same thing here. So you have like that, like that, like that. So this one also cancel off each other because the overall is 0. These two combine to form this resultant, like resultant force, but resultant vector can cancel off each other. Same thing here, cancel off. Okay, here also cancel off. Here also cancel off. Here also cancel off. Okay. Examples of polar moment make up of atoms with different electronegativity. The bond dipole moment do not cancel each other because Cl and F are of different atom of different electronegativity. So there's a net dipole moment. Same for here because this is different from this. Same for here. Same for here, here, and here. Okay, this is a bit bent. So it's not, the dipole moment is not 0 here because of the lone pair. Now, the polar molecule has a distinct partially positive and partial negative region in the structure. So in polar molecule, there's a permanent dipole. Polar molecules subjected to electric field will orientate in a direction opposite to that of the field to minimize electrostatic energy of the molecules. In the absence of the field, the dipoles are behaving in this way. But when it is an electric field, the dipoles will align itself, okay, with the arrow pointing towards the positive plate. All right, because it indicates the movement of electrons. Now, so a stream of liquid that has polar molecules will actually be deflected towards the rock. Now, try this exercise to determine the various polar molecules. You can pause the video. Okay, let's go through the exercise. So for this, we expect an overall dipole moment because Cl and H are different atoms. This one, they cancel each other, correct? This one, polar, because this is not a linear, because you have a two lone pair here. Yeah, so it's a band molecule. So it is not exactly this way. It's not linear. Okay, this one is definitely polar if you draw out the structure. Yep, this and this are different. Now, so this is a flow chart to determine whether a molecule is polar. First of all, ask yourself, is the atoms of different electronegativity? No. Confirm, not polar. Yes. Next question, do the bond dipole moment cancel out vectorially? Yes, non-polar. No, polar. So we have to look at the shape of molecule to help us whether it's band or linear, all right? Now, many covalent bond substances exist as simple molecules. During melting and boiling, the intermolecular forces are broken, but not the covalent bond. To determine the type of intermolecular forces, we need to know the structure of the molecule and whether it's polar. So there are three main types of intermolecular forces that we're going to cover. Instantaneous dipole, induced dipole. We have a short form for this, ID. Permanent dipole forces, PD. Hydrogen bonding, I will just use H bond to simplify. Of course, there are other names you learned before, like van der Waals forces or London dispersion forces. It's actually a general description for both IDID and PDPD. But at A level, we need to specify whether it's IDID and PDPD. So writing this is not sufficient. So if we have non-polar, in general with IDID, polar molecules, IDID, plus PDPD or hydrogen bond. So let's start with IDID, how they arise. The only type of intermolecular forces existing between non-polar molecules is IDID interactions. Okay, electrons are constantly moving. Okay, we know that electrons are not static, they are dynamic, they are always in random movement. So at any given moment, it could be possible that the electron density of the particle can be unsymmetrical. Okay, so you could have the distribution of electrons between two atoms of similar electronegativity this way, but sometimes it can be like that because electrons are always moving. So when the electron density become unsymmetrical or asymmetrical, we call this instantaneous dipole created. The dipole can induce a dipole in neighboring particle. So this results in a synchronized motion of electrons in the two particles, which causes attraction between them. ID-ID interactions are short-lived because the electrons are moving and the dipole vanish and reform. So because of its short-lived, right, the overall attraction is weak. Such ID-ID interactions are caused by momentary movement of electron charges. So they are present between all particles, including atoms, ions, polar, or even non-polar. So this is a diagram to explain the concept. You have symmetrical distribution of electron cloud at the beginning, but when the orbitals overlap, electrons start to move randomly. There is uneven distribution at any instant. So this is one molecule, but there could be another molecule that have this issue as well, that have uneven distribution, creating instantaneous dipole. So there is the instantaneous dipole will induce this dipole. That's why we call it instantaneous dipole-induced dipole forces. Now, these are the factors that affect the strength. When we have a larger electron cloud, they are more easily polarized and distorted. Because more number of electrons means more randomness, right? So more possibility of the electrons moving in such a way that causes uneven distribution. So the strength of ID-ID increases with number of electrons. Therefore, down group 17, we have an increase in boiling point because of the increase in number of electrons. So how do you explain in exam? The halogens are non-polar, okay? So the attraction between molecules is due to ID-ID interaction. So you must acknowledge, number one, they are non-polar molecules, and the dominant FOA, force of attraction or interaction, is ID-ID. And you must also explain that, okay, down the group, the number of electrons increases, and therefore, the ease of polarizability of electron clouds and the strength of ID-ID interactions will increase. You have to mention number of electron increase, so the electron clouds become more polarizable. Okay, so since boiling involves overcoming intermolecular force, so with increased strength means what? More energy. Mention that also. To overcome stronger ID-ID. Okay, stronger intermolecular forces. Okay, surface area. So what if we have two molecules with exactly the same number of electrons, but why one has a greater boiling point? It has to do with surface area. So if you look at this tree, okay, they are isomers of same molecular size, but they have different surface area. So the straight chain one has a larger surface area, while the branch chain has a smaller surface area. So the more branch the hydrocarbon, the lower the boiling point. So straight chain hydrocarbon have greater surface area for intermolecular interactions compared to the branch. So ID-ID interactions are stronger than the branch chain. As branching increases, the surface area decreases, so the boiling point will decrease. Let's talk about PD-PD. Polar molecules have permanent dipole. The molecules will align such that the partially positive end of the molecule is near the partially negative end. Okay, opposite charge attract. Because there will be electrostatic attraction between the positive end and the negative end of the other molecule, which give rise to PD-PD interactions. So for molecules with similar number of electrons, those with PD-PD interactions will have higher boiling point than ID-ID only. But polar molecules have both, just that the dominant one is ID-ID. For non-polar, it's definitely ID-ID only. So the strength of PD-PD increases with increasing dipole moment. So if you compare Br2 with ICL, the electron cloud size is actually similar because they have similar MR, so they will have similar number of electrons, similar but not the same. But the strength of ID-ID interactions are actually similar. However, because iodine chloride is polar, so the intermolecular forces is actually stronger in iodine chloride because they also have PD-PD interactions. If we compare Br2 with ClF and BrF, Br2 is the non-polar, so it definitely have low boiling point. But because you see, it has a large electron cloud size compared to these two. So even though it's ID-ID, it doesn't mean that, oh, it must definitely be of low boiling point. No, okay, it may not be so. Because although these two are polar, but because the electron cloud size is so large, so the ID-ID interaction is so significant, it will constitute a higher boiling point, even though it's a non-polar. So this is a lesson learned. It doesn't mean that, okay, this molecule is non-polar, this one is polar, the non-polar will definitely have a lower boiling point. Not true. You have to see the electron cloud size. You can only compare compounds with similar cloud size, electron cloud size, okay, to compare their melting point or boiling point. Hydrogen bonding is a special type of PD-PD interaction. So how does it arise? So an important kind of PD-PD occurs between molecules containing hydrogen atom bonded to a small highly electronegative atom with lone electron pair. So what happened is that the highly electronegative F, O, and N atoms will cause the electron density to be so greatly withdrawn from the attached H, such that the H atom is left with a partial positive charge. So the resulting FH, OH, and NH bond are extremely polar because the hydrogen is covalently bonded to a very electronegative atom. And the highly positive charged hydrogen atom can form a strong attraction with the lone pair of adjacent molecule. And this intermolecular force is hydrogen bond. Okay, I'll show you the diagram later. The small size of F, O, N are important for H bonding because it makes this atom so electronegative that the covalent bond H has a high partial positive charge. It allows the lone pair on the other F, O, and N to come close to the protonic H atom. So there are two criteria for hydrogen bonding. Number one, the hydrogen atom is covalently bonded to F, O, and N directly. Number two, the lone pair of electrons of F, O, and N atom in the neighboring molecule can attract the partial positive charge of the hydrogen atom, like this. So you have to represent hydrogen bond in this manner. So X and Y are electronegative atoms. So the H is forming hydrogen bond with the lone pair of electrons. So positive, negative, opposite charge attract. The hydrogen bond is often the strongest form of intermolecular force. It is about 5 to 10 times stronger than the PD-PD force. But compared to covalent bond, hydrogen bond is still much weaker. Hydrogen bond occur between the same type of molecules or between different types of molecules containing hydrogen covalently bond N, O, or F. So such compound also contain instantaneous dipole, so that besides hydrogen bond, ID-ID interactions also exist between molecules of this compound. So it doesn't mean that, okay, this molecule has hydrogen bond, it has no ID-ID. No, it also has ID-ID. And sometimes the ID-ID could be more significant, all right? So between HF and HF, we have hydrogen bond. But between HF and water, there's also hydrogen bond, which explains why some substances are soluble in water because they form hydrogen bond. For example, sugar, for example, ethanol. The reason why they are soluble is because they form hydrogen bond with water molecules. So when their interactions is observed as soluble. Now, what are the effects of hydrogen bonding on physical properties? So remember, only intermolecular forces are broken when we melt or boil a substance. The covalent bond is not broken. And intermolecular forces in general increase in strength, with hydrogen bond the strongest. Because with stronger intermolecular force, it requires a greater amount of energy to overcome the force of attraction. So this diagram shows the boiling point of the hydride of group 14, 15, and 16. Okay, now let's look at this graph and make some observations here. For observation 1, let's look at group 14. The boiling point increases in this order with this being the highest compared to this. So group 14 hydrides, they are actually non-polar. If you draw the dot and cross diagram or show the molecular geometry, they are all non-polar. The dipole moment is 0. So the main forces of attraction is ID-ID. Okay, we also accept van der Waals, but ID-ID is preferred. The increase in BP from CH4 to SNH4 is due to the increase in strength of ID-ID interaction because the number of electrons increases. Next observation, we see that here H2O, NH3, and CH4. The highest is H2O, followed by NH3 and CH4. This is the second observation here. So NH3 and H2O have relatively higher boiling point because there is intermolecular hydrogen bond. Intermolecular, okay? There is no hydrogen bond in CH4. So the hydrogen bond will be stronger than the ID-ID forces in CH4. And why H2O has a higher boiling point than NH3? Because H2O has more extensive, this is important, more extensive hydrogen bond in H2O compared to NH3. H2O form more hydrogen bond because H2O can form 2 hydrogen bonds because it has 2 lone pair of electrons of oxygen and 2 hydrogen, which allow this molecule to form a maximum of 4 hydrogen bonds. Okay, so let's say for this one, this molecule here, okay, water, 1, 2, so this is the first one, second bond, then these 2 hydrogen can also form hydrogen bond. This one also can form another one. So maximum of 4 H bonds lah. In contrast, right, NH3 only have 3 H atoms, but only 1 pathetic lone pair. So it corresponds to average of only 1 hydrogen bond of NH3 compared to 2 hydrogen bonds per molecule in H2O. Because this one is actually average of 2 H bonds, not 4. Maximum each molecule can have is 4, but on average is divided by 2. Yeah, because the 4 is between 2 water molecules, so you take 4 divided by 2 to give you 2. Nitrogen in NH3 is only 2. So because only got 1 lone pair, so it's 2 divided by 2, 1. Yeah. So more hydrogen bond need to be broken when boiling water, so more energy required. Now, H2O also forms stronger hydrogen bond between molecules compared to NH3 because HO bond has a higher dipole moment. Okay, this is another key point. Then between NH3 and HF, NH3 and HF, they don't have it here, but we have it here. So between these 2 molecules, right, NH3 has a lower boiling point, although both have hydrogen bond. But this is because HS bond is greater for HF, because F is more electronegative. So the larger the dipole moment, the stronger the hydrogen bond, so more energy to overcome. Let's examine the open structure of ice. Okay, most liquid become denser when they change into solid form. but not so with ice. The lower density of ice is due to the highly ordered three-dimensional structure arises from hydrogen bond. So each oxygen atom in ice is tetrahedrally bonded to 4 hydrogen atoms, 2 by covalent bond and 2 by hydrogen bond. So this arrangement allows the water molecules in ice to form a rigid open three-dimensional network as shown. So this highly ordered three-dimensional arrangement of water molecules creates a very open structure and prevent the molecules from coming close to each other, which explains for its large volume, and hence ice is less dense than liquid water. You can try this question and answer accordingly. So which statement is correct? The answer is B. All right. And you can just read yourself. Hydrogen bond can be used to explain dimerization in some compounds. For example, the molar mass of some carboxylic acid in a vapor phase is found to be twice of this actual molar mass from the molecular formula. For example, ethanoic acid, right, is supposed to be 60 grams per mole, but the gaseous ethanoic acid is determined to be 120. So we need to explain why. Because carboxylic acid is a dimer in the vapor phase, made up of 2 carboxylic acid bonded to each other by 2 hydrogen bond here. So it forms an 8-member ring. 1, 2, 3, 4, 5, 6, 7, 8. So this is an 8-member ring. The carboxylic acid also exists in dimer in some non-polar solvent also. However, when we place this in aqueous solution, no dimerization occurs because the carboxylic acid actually form hydrogen bond with water, which prevent dimerization from occurring. Now, let's look at some organic molecules. We have 2 nitrophenol here and 4 nitrophenol here. Why is there a difference in boiling point? They are actually isomers, but they are different in boiling point and different in solubility. It has to do with hydrogen bonding. Yes, the lower boiling point and solubility of 2 nitrophenol is due to intramolecular hydrogen bonding. Because you see, this NO2 is closer to this OH, so there's greater chance of intramolecular hydrogen bond. So the hydrogen bond is formed between the 2 groups here. We call it intramolecular hydrogen bond. And this contrasts with the hydrogen bond between 2 groups from 2 different molecules. In the 4-nitrophenol, these 2 groups are too far apart from each other. So there is no intramolecular hydrogen bond. Now, due to the formation of intramolecular hydrogen bond in 2-nitrophenol, less sites are available for hydrogen bond with other 2-nitrophenol molecules. Because they form intramolecular, so there is less extensive intermolecular hydrogen bond. So with less extensive intermolecular hydrogen bond, you don't see the bonds here. Because already used here, you know what I mean? So the boiling point is lower because less extensive, less energy to overcome. So these are some other examples. Okay, you can read yourself. Now, so if we compare molecules of similar number of electrons, then the strength of hydrogen bond should be the highest among the 3. Explain why the boiling point of propane, dimethyl ether, and ethanol deviate so greatly, even though the electron cloud size are different. So how do you explain this question? So since the electron cloud size of the 3 compounds are similar, acknowledge that first. You have to say, therefore, the ID-ID interactions is similar. Important. You need to acknowledge that first. Then you say, okay, propene is non-polar, so that the intermolecular force is due to only ID-ID. So it has a lowest boiling point. Dimethyl ether is polar, so there's energy required to also overcome the stronger PD-PD interactions. So the boiling point is higher than propane. And ethanol, even better. It has a hydrogen bond between the ethanol molecules because they have a hydrogen atom that's covalently bonded to the oxygen atom. So there's hydrogen bond in ethanol. So the intermolecular forces in ethanol is strongest. Why iodine has a higher boiling point than water? As we know, iodine is a solid at room temperature. Water is still a liquid. It has to do with the number of electrons. So both are simple molecular structure, but iodine is a non-polar, water is a polar. But still, iodine has a higher boiling point because the number of electrons is much more in iodine. So the ID-ID interaction is even stronger than hydrogen bond. Yes, the ID-ID interactions. So if you have so much electrons, your ID-ID can overtake hydrogen bond. Okay? In general, the solubility of substances in solvent follow this rule. Like dissolve like. A substance dissolves in a solvent if the intermolecular forces in the solute and solvent are similar. So whether a substance dissolves depends on how much energy to overcome the intermolecular forces within the solute and within the solvent, and how much energy is released to compensate for the above energy. So like dissolve like. So if we have simple molecules with the same type of intermolecular bond, they mix well. So for example, hexane as a solvent, iodine is non-polar, hexane also non-polar. So ID-ID for solid-solid interactions, solvent-solvent interactions is ID-ID. So this is a solute. This is how they explain. So between that is ID-ID. So this interaction is favorable because solute-solvent interaction is ID-ID forces, which is similar, like dissolve like. All right, this concept. But for iodine and water, no, because water is hydrogen bond, iodine is ID-ID. This is unfavorable because solute-solvent interaction is ID-ID forces, which is weaker than hydrogen bond. So the energy released in forming bonds between the solute and solvent molecules cannot compensate for the hydrogen bond breaking water. So if you want to dissolve something, there is energy required to break the hydrogen bond in water before that substance can interact with water. If your interaction between the molecules is ID-ID, then there's not enough energy to break the hydrogen bond. So this is the important concept here. Okay, there is energy release when bonds are formed between solid and solvent, but that energy release is not sufficient to compensate for the energy taken in to break the bond. So it cannot happen. Okay, example 2, ethanol is very soluble in water because it forms hydrogen bond with water. The hydrogen bond formed between water and ethanol release energy and is able to compensate for the energy to break the hydrogen bond. So this can work because they are all hydrogen bond and there's enough energy, right, released from the formation to break the hydrogen bond in pure water and pure ethanol. Ionic solid tend to dissolve in water. So when an ionic compound dissolves, we need to break down the crystal lattice, and this requires a lot of energy. And this input of energy is offset by the release of energy caused by solvation. So most ionic solids are usually soluble in water because a lot of energy is released from ions, forming strong ion-dipole interaction. So ion dipole forces attract ion and polar molecule to itself. The strength of interaction depends on the charge and size of the ion, as well as the magnitude of the dipole moment and the size of molecule. So the large amount of energy released in the formation of strong ion-dipole interaction is able to compensate for the energy to overcome the ionic bond in a solid. So if you want to dissolve a substance, you have to make sure that, okay, there is actually energy to break the ionic bond. There's energy required to break the hydrogen bond, okay, both of it. So you need to make sure that the energy released when the ion-dipole interactions are formed is large enough to break this bond. Okay, so ion-dipole interaction is just the water is the dipole. The ion refers to the sodium ion or the chloride ion. Okay, where the partial negative charge of the water attract the positive sodium ion, then partial positive hydrogen on the water molecules attract the negative chloride ions. Okay? But some ionic compounds like magnesium oxide are insoluble because the ionic bonds is too strong and require a lot of energy to overcome. So they remain insoluble in water. All right? So it has to do with bond strength as well. The solute concerned reacts with the solvent, and the reaction products form favorable interaction with the solvent, like this. So the ions formed from the reaction of HBr in water, this can happen because there is strong ion dipole interaction with water molecules. So HBr is soluble in water. Okay, so Br minus can form strong ion dipole interaction with water. Now, you can pause this video to examine this question before we go through the answer. Okay. When two liquids are mixed, heat may be evolved if intermolecular bonds formed are stronger than those broken, even if there's no chemical reaction. Which pair of liquid when mixed will give out heat, which means exothermic lah. Okay, so you have to ask yourself this question. Give out heat, meaning that what's the answer? It's A. Why? Okay, so we have to examine the type of interactions in the molecules. So for A, CH2Cl2 is PD-PD because it's polar. Then this one is also PD-PD, polar. Okay, but for the B hole, cannot because this is polar, right? This is non-polar. So one is ID-ID as a predominant force of attraction or interactions. Non-polar, a polar will be ID. Is PD-PD. And non-polar is ID-ID. So like dissolve like cannot. This like unlike cannot. This one is ID-ID. This one is PD-PD. Cannot. This one is ID-ID. This one is hydrogen bond. Cannot. All right. So only this one, where both are PD-PD. Okay. Last part is on lattice of crystalline solid. So what is crystalline solid? It is a well-defined arrangement and long-range order. Its atoms, molecules, or ions are highly ordered in a regular three-dimension arrangement. The particles in a crystalline solid are arranged in regular geometric pattern that repeat over and over again in all directions. So these are the examples of crystalline solid and their classifications. Their physical properties is a consequence of structure and bonding. All right. So these are examples of ionic lattice, which you learn in secondary school. You learn on coordination number also. And you understand that they are non-directional. There is no preferred orientation where the ions attract the other ions of the opposite charge. We also learn about ionic bond strength. They are very strong and requires a lot of energy to overcome. And the strength of the ionic bond is indicated by lattice energy, where it is the energy release when 1 mole of the ionic solid is formed from its gaseous ions, which we'll learn later under energetics. The attraction between unlike charges will result in stabilization and energy is given out. So the greater the attraction, the greater the amount of energy given out. Conversely, when there are repulsion, there will be destabilization and energy is taken in. So this is a formula that relates lattice energy to charge and radius. So the greater the magnitude of lattice energy, the stronger the ionic bond. And the strength of ionic bond is favored by higher charge and smallest radius or size. Okay, you can try this yourself and check the answer. at your own time. Now, I'll go through this very quickly because most of it was covered in secondary school. It's a recap of what was learned. All right, so you can read yourself the various physical properties of ionic compounds. They are melting point, boiling point, solubility, and ability to conduct. Cannot conduct in solid state. Why? They are hard and brittle. This is also covered before in secondary school. And we also talk about giant molecular lattice in secondary school, that solid with giant molecular lattice are atoms held together in extensive network. This is an important keyword by covalent bond. Okay, diamond. Okay, these are the properties of diamond. They are insulator, strong covalent bond, so high melting point. They does not dissolve in water because the carbon atoms are strongly covalently bonded. Silicon, which is similar to diamond, is also hard, but because silicon atoms, the bonds between them are weaker, so you expect it to have a lower melting point. Another answer is the orbitals of silicon are larger and more diffuse than carbon. So the effectiveness of orbitals overlapping is poorer in silicon, resulting in weaker covalent bond. Graphite, we covered this in O level. And what is new is the sigma bond. Only this is new. And the trigonal planar, okay, within the layer and the bond angle, this is new. And the carbon atom, the electron that's not involved is actually in the p orbital. So what happens is that the p orbital of the carbon atom will overlap collaterally with the p orbital of its immediate neighbors. And this will result in an extended pi electron cloud below and above the plane. Okay, so the electron that's not involved in bonding is in the p orbital of the carbon atom. So they will actually overlap with other orbitals of other carbon and form extended pi electron cloud. And the electrons are delocalized over the whole layer. Therefore, graphite is an electrical conductor. And the pi electrons are only able to conduct within the layer because that's where the pi electrons are delocalized. The attraction between carbon atoms within each layer is due to strong covalent bond, but between layers is weak IDID. So you learn van der Waals forces in secondary school, so change it to IDID now. And these are what we learned, and I'm not going to go through it. Silicon dioxide and simple molecular lattice, specifying iodine. Iodine is a solid. Many people actually doesn't know about it. It's still IDID interactions, by the way. And we also talk about the solubility, that it can dissolve well in organic solvent because both are non-polar and they do not conduct electricity. Giant metallic lattice, the last one, metallic bond. I shall not go to it anymore. And what are the factors affecting the strength of the metallic bond? It is determined by the number of valence electrons. The more, the stronger. The size of the cation, the smaller, the stronger. And the physical properties of metals, you can just read through yourself. It's exactly the same as O level. And this is just a summary of the lesson. Okay, and that's it. I hope you learned a lot today, and please revise the important concepts at your own time. Thank you.